Hey, you guys. Here's our last bit of Chapter 7, Sections 6 through 9 about quantum theory and the electronic structure of atoms. We've had a lot of questions. We had all of these questions that we focused on. What it is, how does it travel? We had lots of formulas that we used in order to describe this stuff. What we're going to be looking at now is the where is an electron in an atom, again, because we talked about that already, but from one angle of one theory, and how does an electron move? Now we talked about how did it move. It was like a wave in there, but now we're going to look at Schrodinger's equation and a little bit of the uncertainty principle again, but mostly just the Schrodinger equation of how does an electron move and what are its defining characteristics. And I'm talking about the electron. What are the electron's defining characteristics? So let's talk about the Schrodinger wave equation and what that means. This wave equation, this is all around the same time. You can see de Broglie was 1926, Schrodinger's 1926. I'm sorry, de Broglie was 1924 on our previous slideshow. Schrodinger wrote an equation, or kind of proposed an equation that described both the particle and wave nature of the electron. Because remember, I could pass an electron through an aluminum foil and I would get these circles, and that circles meant it was traveling like a wave. And this equation that he wrote included what was called wave functions. And those wave functions describe the energy of the electron with a given wave function and the probability of finding the electron in a volume of space known as an orbital. So this equation was analogous to Newton's laws of motion for macroscopic objects. And we're not going to go through all the math of that, but the end of the day was, see this GIF down here, this is showing the electron kind of jumping all over the place. It has particle nature, but it also has wave nature. And it also describes the probability of finding an electron in a volume. And you can see a volume here. And in this one, you see like a circular volume. It doesn't look like there's anything in the middle, but it looks like it's tracing out a space right around here. So that's going to be a certain area of where the electron is found. And that is known as an orbital. And orbitals are mathematical solutions to this equation that actually show a shape. And I don't know if you remember from algebra or whatever, you could have a graph and you could have a line, and that was a y equals mx plus b. Sure, that would describe that line. And then you would have other types of equations that would describe, say, for example, a parabola or an exponential decay. Those all have equations, and they're mathematical equations that describe a graph. So this is the same thing. It's a mathematical equation that describes a shape. So the Schrodinger wave equation tells us about these quantum numbers. They're the solutions. These four quantum numbers are the solutions to the Schrodinger wave equation. The first quantum number is called n, and that n is the principal quantum number, and it is its distance from the nucleus. So I'm showing you what's called 1s orbitals, and the 1 is a quantum number that's closest to the nucleus. 2 is a bit further away, and 3 is even a bit further away. So you can think of the nucleus being in the center of all these, and that the quantum number for each just tells you what's the probability of finding an electron in this space. So those are three different quantum numbers as far as n1 through 3 for the s electrons and the shape that the Schrodinger equation is predicting. Let's go on to our next piece. This was n, and then n was the principal quantum number, said how far away it was from the nucleus, if this was the nucleus. This L is going to describe the angular momentum. It's called the angular momentum quantum number. And those values are numbers, that's true, but they describe a certain thing. There's certain rules for these numbers, and those rules are if n, whatever n is, L has to fall into a certain values. So if n equals 1, L can be 0 to n minus 1. So if n equals 1, L can be 0 to n minus 1. So if n equals 1, L can only be 0 because 1 minus 1 is 0, and that's an s orbital. If n equals 2, L can be 0 or 1, and that means there are s and p orbitals in the second level. It's 2. And then if it's 3, it can be 3 different values, and that means there's s, p, and d orbitals shape-wise. And these are different shapes. S's are spherical in shape. P looks like lobes that go down to 0 in the center. And then D have all different shapes, and we're going to look at those here in a second. So there's our S, there's our P, and there's our D, and there's our F. So these are the shapes. So this second quantum number here, L, it describes the shape of the orbital in which the electron may be found. So here's our s orbitals, and that's what we saw in the previous slide. And there's our p orbitals, and that's what they look like. Like I said, it's kind of like a lobe, and it goes down to 0 in the middle. So this d orbitals, again, kind of weird shapes. These lobes are in between the axes on some, and they're actually on the axes on others. And then you have this kind of strange shape that is traced out in the 3dz squared orbital. Now again, these are coming from the Schrodinger equation, and they are shapes that are described by that equation that then dictates where the electron can be found. So our m sub L is called a magnetic quantum number, and for a given value of L, like we were just saying, like if L equals 0, that's an s orbital, the given values of m sub L are negative L to positive L. So if L equals 0, it can only be 0. So if L equals 1, it can be negative 1, 0, or positive 1. But these numbers are just numbers. They are just indicators of it being different than another one. So don't get too worried about what the numbers actually are. They're just kind of ambiguous assignments to make them different from another one. And that's because no two electrons can have the same 4 quantum numbers because they can't be the same electron. So having these different assignments helps differentiate that. So if L equals 1, these are the possibilities. And I don't know if you remember, there were 3 p orbitals, px, py, and pz. There were 3 of them. If it was d, then there's 5 different orbitals. And so this quantum number, magnetic quantum number m sub L, describes the orientation of the orbital in space. So there's our 3 orientations in. There's our 3 orientations in space of the p orbitals. So you have a px, a py, and a pz. For d orbitals, we have 5 orientations in space. And don't worry about really truly understanding what this is. Just realize that it is different shapes that are described by the equation that the electrons are allowed to occupy. So this is something that is online. It's a YouTube video that goes through and shows the overlap of the different orbitals. So as far as a 1s orbital, here it is. It's 1s, it's small, it's in the middle, and if you have an electron, one electron, say in a hydrogen atom, like 1s1, it will be in there. Now this is showing the overlap of the 2p orbitals on there. So that means there was a 1s, a 2s, and then the 2p's. And this video shows the overlapping. This is now putting a 3s on top of it. And the 2p's and the 2s and the 1s are inside there. And then this is showing it looks like the 3p orbitals are put on top of. And this is like a nesting doll. That's what I always call it. Because a nesting doll has different shapes, but they nest inside of each other. It actually has the same shape that can nest inside of each other. So that was the 3p. This is the 4s now being overlapped on top of that. And this is the 3d being overlapped on top of the 4s. So the 4s is in here. You can see that. And then this is the 3d. And they've all been overlapped. And if you look at this as a whole, the atom does look like a sphere. And that's because they all overlap each other and those electrons are inside there. So the Schrodinger wave equation tells us these quantum numbers. We're now on the last quantum number, which is the spin quantum number. And that's because electrons actually have spin, they're particles, and they are spinning either to the one way or the other way. And a spinning charged particle will end up with a north and a south if it spins one way, and a south and a north. Because remember, a spinning charge creates a magnetic field. So they're like little tiny magnets. So when you have 2 magnets, they have to be north-south and south-north to be living in the same box. So what ends up happening here is that an orbital can only ever hold 2 electrons because one's going to be up, one's going to be down, meaning the north-south and south-north. So there's our plus and minus. And it's just indicated by plus 1/2 and minus 1/2. And this is a picture out of your book of which there was an experiment that was done in order to determine that electrons indeed have spin associated with them. And that means they're like little spinning charges. That means they have an electric field and a magnetic field. And that means you put them in the presence of a magnet, and sure enough, they will respond by being deflected. So as an example, let's do example 7.7. Let's list the values of N, L, M sub L for orbitals in the 4D subshell. So 4D, that gives you information. And there's our way we're going to write it. So N's got to be 4, hence the 4 in front of the D. And L, this is an L, can be 0, 1, 2, or 3. Now, which one we choose depends on which orbital it is. It's a d orbital. And since it's a d orbital, that L value is going to be 2. The M sub L can be all of these values, and you just got to pick them. So there's those values. We just did an example on the previous slide that if you had a 4D electron or electrons, then you could say what are the 4 quantum numbers, and you would have N would be 4, L would be 2, D can either be 0, it can be -2, -1, 0, +1, or +2. And then the final one can be plus or minus 1/2. So you can see if I just choose one of these, like 4, 2, -2, and a +1/2, that is 1 electron in the 4D orbital. So D orbitals can hold 10 electrons. So if I have 4D and there's 10 electrons in there, that means all those 5D orbitals are full. And in each orbital, they have electrons that are opposite in spin, and that's where they are living. So this picture is showing what's called an orbital, right? An orbital is a probability function that it's most likely to be found in a certain area. So in this example, that certain area is the green, right around the center. So this table out of your textbook, table 7.2, the relationship between quantum numbers and atomic orbitals. The quantum numbers tell you something. N equal 1, L equals 0. This is an s orbital. This has to be 0 because it's an s orbital. The number of orbitals that have this designation are 1, and that atomic designation is 1s. So if I write 1s2, I'm just indicating to you helium, because helium has 2 electrons in the s orbital. So that's what this table is trying to just go through. It's just showing you what is the relation between quantum numbers, these are the quantum numbers, and the orbital designation. So this is a video that is off of YouTube, and it's kind of neat because they go through showing all the different orbitals, but I don't know if it's going to play. So I'll go ahead and try, and if it doesn't, we go to the next slide, then I'll go ahead and put this out as an announcement. There it goes. It looks like it's playing. I can see it playing. And this little video, whoever created this, is kind of neat. They're going through showing the atom. Look at the top. They're talking about the Bohr theory of the atom. But then Heisenberg said it was more like electrons jump around the nucleus, Heisenberg's uncertainty principle. There wasn't a location and a momentum. So that's a kind of a neat little periodic table of orbitals, and it shows you the different shapes. Now it looks like they're going to choose an atom. This is helium. Helium has 2 electrons in there. And you can see they're both in the 1s orbital. And you can see the nucleus has 2 protons and 2 neutrons. So that's helium. Then they're going to build it a little bit larger to beryllium. Beryllium is 2s2. So it's got 2 electrons in the s, 2 electrons in the 1s, and 2 electrons in the 2s. Now they've gone to neon. And neon has filled 2 p orbitals. Those 2 p orbitals are those gold ones. Now we're going to go to sulfur, and sulfur has filled 3p, mostly filled. It has some 3p orbitals, and they're somewhat filled. And you can see it's like a nesting. And now this one is iron. and you can see D shells are filled. So I'll post the link for this, but that's all it was this person doing this and going through all these things. I'd like to be able to do this myself, to play around with it and post it for you guys. This is a video of somebody doing this. So let's move on. So this was showing orbitals, and it was showing the electrons kind of jumping around in those orbitals that you can't really know where they are. They're just kind of everywhere, but their highest probability is in whatever orbital they happen to be in. So the energy of these orbitals and the electrons in the orbitals is from low to high. And this low starts with 1 and an S. So the energy of the electron only depends on where it is. So the lowest energy is the electron in 1. And this is for in a single electron atom. And you say, how do you know that? Well, this is because of the solution to the Schrodinger equation gives you information. But it turns out other solutions, when you have multi-electron atoms, does not follow this same pattern where the 2s are in line and the 3s are in line. So this is the energy of an electron in a certain orbital. So this n equal 1, n equal 2, this is what we were talking about before, that's the energy. This is the n value that you would put here. This is the Rydberg constant, which is in joules, and that's the amount of energy of that electron in that orbital. But in a multi-electron atom, the energy values change a little bit. You can see a p is slightly higher than an s. And I don't know if you remember the drawings. We did a 1s, and then we did a 2s, and then we did 2p's. And those 2p's were a little bit outside the s's. And I think that's because of the energy being slightly higher. So energy depends on both on n and L. Remember, n was the principal quantum number, n equal 1 down here, and L was the which orbital it was, like S versus P, or S versus P versus D. So the way that this is set up is that, or not that it's set up, is that it's, we observe the universe, and the universe shows that the electrons have certain energy, and that energy is dependent upon their N and L. So what it is being shown here is the different N values and the different L values. So here we have L equals 0, it's an s orbital. We have L equal 1, it's a p orbital. And then we have L equal 2, and it's a d orbital. They all have different energies. And the energy values for the orbitals themselves is S has a lower energy than P, which has a lower energy than D, which has a lower energy than F. And that's why it fills up in that way. S fills, then P. S fills, then P, then D. But what's kind of weird here is it goes over to S because of the D ends up having a higher energy than the previous S shell. So to this fill-up method of electrons, as far as an electron configuration, there's a filling up method. It's called the Aufbau principle, low to high. And if it's a 1 electron, it would be in the 1s shell. And there would be the electron configuration of hydrogen. If it's helium, it's got 2 electrons, the other electron must go into that spot with the 1s electron, the other 1s electron, plus 1/2, minus 1/2. Now lithium has 3 electrons, so we're going to have to break into the next level. And there's the electron configuration for helium. Beryllium has 4, so you have to double up. There's the electron configuration for beryllium. So this just keeps on going, and I keep on going across the periodic table. That was boron. There was carbon. Now on carbon, where should it go? Since we're in the same level here, can it go in the same one, or should it go in a different one? And that's Hund's rule. The most stable arrangement of electrons in the subshells is the one with the greatest number of parallel spins. So in our situation, when we were thinking about this down here, we should put them in different orbitals with parallel spins. So how many parallel spins does this have? I guess this one's going up, and that one's going up also, and then these 2 are going up. And there's the electron configuration of carbon. But when you draw the orbital diagram, 1 up, 1 down, 1 up, 1 down, it's a 1 up and a 1 up. Nitrogen, 7 electrons, you put a 3rd one into there. Oxygen has 8, so you can see how this is just this fill-up method. Fluorine has 9, and there's its electron configuration. Neon has 10. So now it's completely full. So this is another way to look at the order of filling using the periodic table or using this type of drawing is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So when you draw this, I mean, you could just write it out. 1s, 2s, 3s, 4s, 5s, 6s, and 7s, and then put your little arrows, and that tells you how they are filled up. And there's the order of energy down here at the bottom. The lowest energy orbital is 1s. The highest energy would be 6s. So these quantum numbers, as far as the shells that they're in, a shell is an electron with the same value of n. So n equal 1, and then you have the next shell, n equal 2, and then n equal 3. So those are shells. They have the same n value, but a subshell is something like s's and p's, the same value of n and l. So a subshell is like s, and p, and so on. An orbital is an electron with the same value of n, l, and epsilon l. So if I have a 4s orbital, they will have electrons. So if I put a 1 here, that means the n is going to be equal to 4. The L is going to be equal to 0. The M sub L is going to be equal to 0. And then I could just choose whichever spin I wanted to. So let's do a quick couple examples here. How many electrons can an orbital hold? Well, it depends. Actually, it doesn't depend. It's always the same answer. One orbital can hold only 2 electrons if everything else is fixed. If n, l, and m sub l are the same, it can hold 2 electrons. So it's either plus 1/2 or it's minus 1/2. So that's what you're seeing here, plus 1/2 or minus 1/2, and that's the 2 electrons. So that's the end of the day there. So how many 2p orbitals are there in an atom? Now, as far as a 2p orbital, remember you have a px, py, and a pz. For n equal 2, L equal to 1, and there's the 3 different orbitals, and that's what that's saying. So that means in the 2p shell, 6 electrons can be housed. How many electrons can be in a 3d? If you remember a 3d, the n equals 3, and if it's a d, L equals 2, and that means your m sub L values can possibly be 5 different values, starting -2 to +2. So it can hold 10 electrons. So as far as these quantum numbers, we're just continuing on with the quantum numbers, n, l, m sub L, and m sub s. The existence and energy of electrons in an atom is described by its unique wave function, and that wave function depends upon those 4 numbers. So no 2 electrons can have the same 4 quantum numbers, and they have that means each electron has its own energy. But some have the same energy, I think, because you have like a 2p orbital, and you can have energy of n electrons in here. These are called degenerate orbitals, which means they have the same energy. So as far as the energy of an electron is described by its wave function and its 4 quantum numbers, but it's also described by like where it is as far as with other electrons. So the 4 quantum numbers are like a zip code for each element in an atom. And this Pauli exclusion principle I stated earlier, that no 2 electrons in an atom can have the same 4 quantum numbers. That makes them unique. So the electron configuration shows how the electrons are distributed. 1s1 would be hydrogen. And then an orbital diagram is the boxes with the arrows. So this is hydrogen, he's 1s1. There's the principal quantum number. S indicates the angular momentum quantum number. And then the arrow indicates its spin, whether it's up or down. But I don't know whether it's positive or -1/2. I just know it's one of them. So there's that spin now that we were already talking about, but this paramagnetic, since these guys are like little spinning magnetic particles, that if they have unpaired electrons, if there's unpaired electrons in an atom, that means their magnetic fields add to each other. And that's called paramagnetic, and paramagnetic is an atom that has unpaired electrons. It responds to a negative field. So a paramagnetic substance, you lower it down in the form of electromagnetic, in an electromagnet, it will respond. Diamagnetic is where all electrons are paired, and that means it will not respond to a magnetic field because all of the little magnets kind of cancel each other out. So as far as writing electron configurations, just look at your number of electrons in your atom. If this is magnesium, he has 12 electrons. And since he has 12 electrons, we can just start filling up from left to right. 1s2, 2s2, 2p6, and then 3s2 stops at magnesium for a total of 12 electrons. And it can be abbreviated using this core method. Neon is the previous noble gas, and then 3s2 would be finishing it up. What are the possible quantum numbers for the last or outermost electron in chlorine? Well, you would need to know what chlorine is. Chlorine is 17 electrons. You need to know his electron configuration, and the electron configuration shows electrons being added to the 3p level last. So as far as possible quantum numbers for that last electron, n is going to equal 3 because of the 3. L is going to equal 1 because it's a p orbital. M sub L, you could basically choose anything from -1 to +1 with a 0 in between. There's 3 different of those. And then M sub S, just choose one, positive or -1/2. And that's what that's showing here. So that last electron is added to the p orbital, and that's why I chose that one too when I was talking about that a moment ago. So there's your n equal 3, L equal 1, and then M sub L can be all those different 3 values, and then M sub S can be one or the other. Now, as far as how that's done, I mean, we look at this is the periodic table, and as you read from left to right, you think about cutting this box in half. This is magnesium, that's one we just did. So it would be 1s2 is filled, 2s2 is filled, and then 2p6 is filled, and then 3s2 is filled because it's magnesium. And then I stop right here. If I was going on to the next one, on 3 here, which is aluminum, it would be 3p1. This is a table in your textbook, is all the electron configurations of all the elements on the periodic table. So you don't ever have to do one. You can go look it up. But the goal is to understand what this table means and what the electron configurations mean. Now, there are some weird anomalies in here that kind of don't make sense. And here's silver. Silver is one of them. Silver. We should also have copper is one of them, but copper is not on here. Gold is number 79, and it is not on here either. But copper, silver, and gold are in the same column. And you'll notice instead of, there's a 1 here in the s orbital, instead of being 5s2, 4d10, I'm sorry, instead of being 5s2, 4d9, it's a d10 and a 1. And that's because the energetics of the electron arrangement of the atom is that half-filled or full orbitals are more stable than not half-filled or full, if the atom can accommodate that. So in our silver, we see that by taking one of our 5s electrons into the 4d shell, we can make the 4d full, that is stable, and we can make the 5s half full, which is stable. So go ahead and work on your think sheet number 11 through 15, and that finishes up the fun sheet for chapter 7. And put that in the assignment folder when you're finished.